Good morning, all of you. So today we are going to see about actually the concept evaluation. But before we venture to that, there were many doubts asked about the term assignment 3. So I thought I'll clarify certain issues. First, the major task to be performed as part of the assignment is designing the bridge. Okay, what is given in your assignment sheet is only a suggestion. Okay, it is not even a suggestion, it is only a very schematic arrangement of things. So, completely you have to disregard that. The primary task in the assignment is to design a bridge. How the sticks are going to be arranged to arrive at a maximum load carrying capacity and to cross a span of 0.6 meters is the task assigned to you. Is that clear? Because some express doubts that the design is given in the assignment. No. You have to arrive at a design. The design can be many. There are many options available for you. This is one thing I wanted to clarify. Number two, that is the design part. I will also provide few more inputs regarding the design part. I would suggest that you look into a mechanical structure called a truss. There is an important mechanical structure called a truss. Have you heard about it? Trusses? Have you studied? Gunasekar, the latecomers can please be noted down. Preferably they need not be allowed inside. Okay, the time is already 11:15, they need not be allowed inside. Let them go. Today I would like to spend some 10-15 minutes on the idea called the truss. Okay. All of you must have gone to Engg station. Yes? Without anyone who has not visited Engg station? Okay. Now if you see the whole structure, what is special about the structure of the roof in Engg station? Can somebody say? What is special about the roof in Engg station? Is it a concrete roof? Okay. Sheet protects you from the sun. But what is the structure? What takes up the load? Can you tell me what takes up the load in the whole structure? Is it beams? So you have roughly a mechanical structure, something like this. You have some mechanical structure like this, which takes up the load. You have many such repeating structures and you have a roof. This particular mechanical element is called a truss. Okay, but I cannot ask you all to visit Engg station and see this again. Probably when you go there next time you can look up and see what the structure is. But I can always request you to, while you are going out of our college today evening, you can just see the bike stand very close to the entrance. It is an asbestos sheet stand. Okay. What supports that asbestos sheet? Something like this supports the asbestos sheet. This is again a truss. Now of course, if I start talking about the truss and the beauty of designing the truss, okay, I'll be taking up a lot of time. Please remember, this is completely different from, this is completely, see, this is going to be fixed. This is one pole, there is another pole here, you have a truss. See, the basic problem, in the last class we talked about the different types of trusses coming. One basic problem in construction is all the structural materials like brick, concrete, etc. they are very poor in performing under tension, but they are extremely well under compression. All the structural materials, they are very, very weak in all the structural materials like, not steel, steel is almost equally good on both counts, but concrete, stone, brick, all these materials, they pour very badly when subjected to tension, but they are reasonably good under compression. So the major challenge in designing the members is, you have to avoid, in structures, you have to avoid a brittle material, a construction material like stone or the stone or concrete getting subjected to tensile load. This is a design problem which we have to keep in mind. Okay? People have solved this problem. This is a sort of a perpetual problem for a civil engineer. This problem will exist forever. Over different periods of time, they have evolved different solutions for this problem. The construction materials, they are very poor in tension, they are reasonably good in compression. How people solve this problem over the period is something worth studying by itself. At one point in time, they have designed, the humankind has designed what is known as an arch. The arch design is a very ingenious way of avoiding tension to any construction material. See, can I have a scale please? 1 foot scale, anyone have it? Quick. Now the problem is, you have in construction, columns are not big issues. Columns are subjected to primarily compressive load. Columns are subjected to primarily compressive load. The problem comes with beams. You have a lot of beams, is it not? Now take this is to be a beam. Now you are going to have a lot of loads acting on it. The beam is getting stretched. Yes or no? The beam under load, how will it bend? It will bend like this. I am exaggerating the bending. Of course, this beam is not bending so much. I am exaggerating it. Now, please visualize it carefully. The bottommost point on the beam is subjected to. No, the bottommost points of the beam, these points are pulled apart. They are subjected to tension. On the other hand, the topmost points of the beam are subjected to compression. These points are brought together. If I enlarge, if I exaggerate this beam and then draw, I'll have something like this. If I exaggerate this beam and then draw, this is the original beam. Okay. After deformation, the beam will become something like this. Now you can see the 2 points here were stretched apart. That means the bottommost layer is subjected to tension. These 2 points have come apart. They got separated more. On the other hand, 2 points here, they are pushed together. Are you able to visualize this? So, when in a beam, you have both tension and compression coming in. But tension is not permissible in any construction material. Believe me, that is why they are having steel reinforcements in the modern day beams. In modern day beams, you have concrete which is reinforced with steel. In bridge construction, even steel reinforcement is not good enough. That is why all the bridges of say 40-30 years back, they were all made up of all steel constructions. Just reinforcing is not good enough, because in bridges you want to have a large span. The distance between the two columns you would like to increase, in which case just reinforcement is not good enough. It is worthwhile going for an all steel bridge. So the bridges of yesteryears were all steel bridges. Then you have the bridges. Now the problem today, we were able to use reinforced concrete bridges because we use a new technology called pre-stressed beams. Okay, what you see today, you have steel wires which are stressed in tension and they are released. What these steel wires will do is, they will compress the concrete. So when the beam is not loaded, when the bridge is not loaded, the beams are loaded in compression. Like what you did in your bicycle spokes. What you did in your bicycle spokes? The bicycle spokes, they perform reasonably well in tension, but in compression they may buckle. So what you did was, you applied a tensile load to them. So any compressive load that comes must first neutralize the existing tensile load, then only it will act. A similar strategy, but what we here do is, you pull the steel ropes and release them. So when the beam is not loaded, what these steel ropes will be doing? They will be compressing the concrete. So the concrete is loaded in compression. So when they are used in bridges, so any tensile load that comes must first neutralize the existing compressive load, then only there will be some tensile load coming. So that is the technology that is used today. But what people would have done 100 years back, 200 years back, 300 years back. There also you had constructions. You should have had beams. Okay? Because without beams and columns, believe me, there is no construction. So the one solution to this particular problem is the design of an arch. In arch, again, the vertical load is transmitted as pure compressive load to different structures. I am not going into that. Someone interested in it can further study about the design of arches. How the arch design had evolved over a period of time. Okay. Now, what I wanted to say today is, when you want to design a bridge, you have to design a bridge with a stick, with the ice cream sticks. When you want to design bridges with ice cream sticks, you have to look at the truss designs. Please look for the various designs that are possible in a truss, and then from that you try to get some inspiration. Basically, of course, we will be taught about trusses later. I'll just mention it for 2-3 minutes. Basically, there are three types of trusses. One is a truss which is built like this. I basically start with a triangle, I redo it again. I start with a triangle, add 2 more, add 2 more, add 2 more, keep on building triangles. A triangle is a stable structure. A triangular structure with 3 pins is a stable structure. On the other hand, a rectangle is not a stable structure. If you construct a rectangle with 4 sticks, it is not a very stable. Imagine this being pins. It can tilt either way. It can become something like this. It is not a very stable structure. So a square or a rectangle is not a stable structure. On the other hand, a triangle is a stable structure. I start with a simple triangle, I can keep on building. Or there is another way of doing it. This is one type of truss. There is another way of doing it. That is, you start with a huge triangle. You start with a huge triangle and construct smaller triangles inside it. Is it okay? You start with a huge triangle and have smaller triangles constructed. The whole arrangement can be on a straight line or on a curve. Can also be, the huge triangle can also be on a straight line or on a curve. It all depends on your choice. So these are, I have not given you any design. I have just suggested the approaches, that the various options that you can think of for your bridge design. Internet gives you a much higher exposure to the various designs that are possible. You have 4 days holidays. Try to make optimum use of that and then come out with your design and fabrication during this period. Is it okay? Now, coming to the second point, the first aspect is the design. The second aspect I wanted to highlight was about fabrication. Please believe me, the challenge in proper fabrication is the joint. How you are going to effect the joint. That is the most important aspect. Try to think of some sort of fixture. I don't know whether you understand the term fixture. Some mechanical design which will ensure that these parts are kept together for long period of time. Do you understand? These parts are to be joined together properly. A simple device is, there will be a clip for holding papers together. The paper binder, that clip can be applied at a joint when it is permissible. That is the simplest. Or if you can plan further, there is a mechanical element called a C-clamp. C-clamp. C-clamp can be used. It is available in all the labs. It is available, I think, in the design appreciation lab also, but not in large numbers. Okay. So you can use this clips. Something which will hold them together. That is the secret of making the joint. And the rest I leave it to you. Any other doubts you have regarding the assignment? Then I can quickly go to the, yes? Anything? Right. In which case, we come to the topic of today's discussion, which is on concept evaluation and selection. Now, today's topic is on concept evaluation and selection. Now, in the last, in our discussion last week, rather, we have seen how concept generation can be done. So we have the technique to generate the various concepts for solving a particular design problem. Now, having generated multiple concepts, I should be able to evaluate these concepts separately and then arrive at, and then I should be able to choose a particular concept which will be a solution to the problem. The solution to the design problem. Next slide, please. Now, what is evaluation? Here, what do we mean by evaluation? Evaluation meaning you all know, but here evaluation has a special meaning. Here we mean by evaluation comparison as well as decision making. Okay. Any evaluation is a comparison process. For example, I evaluate your answer states. I have a standard answer in my mind or in my paper. Okay, I can prepare a key and then keep it as a standard answer. I compare the two answers and then decide how much this is close to the correct answer. And then about marks. So evaluation is essentially a comparison process. In benchmarking, you compare your product performance with the performance of a competitor. When you have multiple options, what you do is you compare them with a standard reference, or you compare it with the standard reference, or you compare it among the various options. Competitor doesn't exist here. You are not doing benchmarking. There are absolutely no issue. You can commit mistakes. Okay. We are not doing benchmarking. You have just missed the context. The context here is you have generated various options and you are comparing the options. Yes.
Difference between benchmarking and evaluation.
Okay. Benchmarking is a specific terminology reserved for comparison of your entire product performance along with it is compared with the competitors' performance. You have a product, you want to benchmark it with your competitors' product. Generally, benchmarking is done for the whole of a product. Now we are at a different stage. We are in a stage wherein you have the various sub-functions are represented as black boxes. We need to find solution to these black boxes. Convert electricity into torque. That is what your functional decomposition says. How to convert electricity to torque? How to convert electrical energy into torque? Motor is one solution. There can be multiple solutions. So these solutions we have generated. How did we generate? We generated through brainstorming. We generated these multiple solutions through what is known as 6-3-5 technique. We have generated these multiple solutions. Now I want to compare these multiple solutions and then choose a one which is going to be part of my product. That's what we are discussing. Have I answered your question? Good. Next. Now there are basically 4 evaluation techniques that I am going to present today. The first one is called Feasibility Judgment. The second method is called Technology Readiness Assessment. The third one is called Go, No-Go Screening. The fourth one is called a Decision Matrix Method. Let's see about all these techniques and some of the techniques. Please remember in engineering design concepts we are studying certain tools. These tools may be used in multiple situations. In multiple situations. For example, what we have discussed about brainstorming. Where did we use brainstorming? In concept generation. In concept generation, we have used brainstorming as a tool to generate ideas. Is it okay? But can we use brainstorming in some other situation? Yes, brainstorming as a tool can be used in multiple situations. You have a difficult decision to make, you can resort to brainstorm. An organization has to make a critical financial decision. For decision making, you can use brainstorm. Organization needs some new ideas for breaking a particular problem. You can use brainstorm. All that I am trying to say is what we are studying here in this paper are certain tools. These tools can be used in many situations. Is it okay? Now, for example, the technology readiness assessment is a very very valuable tool, and this can be used in many problem solving situations. I'll explain about it when we discuss that in detail. So these 4 evaluation techniques we will be discussing in detail today, and that will be our agenda today. Apart from that, I have another product case study which we will discuss at the end of the class. Next slide please. Feasibility judgment. Now feasibility judgment is you have various options available. You have an expert as part of the design team. He evaluates the various options and then categorizes them into 3 cases. Something which is not feasible at all. Something is feasible but the feasibility is conditional. Then something which is worth considering at the face of it. You have various options available. There is an expert in your design team, a single expert or a group of experts. They categorize the various options. They categorize the options as something which is not feasible at all. They want to reject it outright. Okay. Now, some things which are conditional, then few things which are worth considering. Now, before we proceed further, we have to understand one important aspect at this particular stage of the design process. Now, imagine you are the decision maker. You are a design engineer. You have generated multiple options. Please understand, design is an iterative process. What do I mean by iterative process? Do you understand what is an iterative process? Yes?
Cyclic.
Pardon?
Cyclic process.
It is cyclic process. It repeats many times. Someone else here said, it repeats many times. You design, you build, you test. This cycle has to take place. Design, build, and test. This keeps on happening. This keeps on happening not once but many times. You design, you build it, you test it. After testing, you find some lacuna in it. You correct it and redesign it. You rebuild it, you retest it. See, a product is not realized in one cycle. A product is realized, the final design of a product is realized over multiple cycles like this. Do you understand? So, at one point of time, you have various concepts before you. As a design engineer, many times it is worth pursuing more than one option and then take a final decision during the course, during the design course. Because if you reject certain options altogether and then proceed with a single option, if that single option fails, what is that? If that single option completely fails, then you may have to revert back and then you may lose a lot of time. So many times you must consider multiple options, you must pursue multiple options, and then at some point of time, as options mature, as these options grow, you take the most promising one, disregarding the least promising. So this depends on the company policy. Many individual companies have to take. See, people simply used to say, don't keep all your eggs on a single basket. Don't keep all your eggs on a single basket. What is the rationale behind it? If that basket goes, then all the eggs are gone. Okay. So when you have are not very sure at the initial stage, when you are not very sure, okay, you keep multiple options available for you so that you can evaluate and take a final decision at a later stage. You can evaluate and take a final decision at a later stage. So, feasibility judgment, it depends on the individual. He frames an opinion whether a particular idea is feasible, whether it will work under certain conditions, whether it is worth considering at the face of it. He categorizes the idea, rejects many, he considers few and then proceeds further. The better experienced the person is, the judgment will be more sound and it will be beneficial to the organization. It is left to the individual's discretion. That is the biggest weakness of the feasibility judgment. Next slide please. The technology readiness assessment. Here, the technology readiness assessment, it is asking 6 important questions. In the technology readiness assessment, it is asking you 6 important questions. This is a very general tool, please believe me. This is not a tool which is developed exclusively for concept selection. No. This is a very general tool. It can be used in multiple situations. I will give you a few examples. Now, can the technology be manufactured with known process? Whenever a company or an organization wants to embark on a new technology, whenever an organization wants to embark on a new technology, it has to make this assessment, the technology readiness assessment. Can the technology be implemented or manufactured with known processes? Is it okay? I think an altogether new technology. For example, LED lighting is a new technology. Okay, you use light emitting diodes, okay, for lighting purpose. Okay, earlier what did we use? We used incandescent lamps, we used fluorescent lamps. Okay, now what is the in thing? The new technology is the LED light. Okay. Now, can this technology be realized with known processes? Can we manufacture huge number of LEDs? First of all, these are the basic units. Okay. Now the second question is, are the critical parameters that control the function identified? Any product, it is undergoing a process. There is a process happening within. So when the light is emitted by an LED, there is a process going on within. First, is this process completely understood? That is very, very important. Because I want to ultimately control this process. Now, let us start from the beginning. Is the functioning of an incandescent bulb, is it completely understood? How does an incandescent bulb function? Let us come to LED later. Because all technology is easy to understand. How does an incandescent bulb function? How does an incandescent bulb function? Can you tell me? Yes? Tell me something. Don't know. How does an incandescent bulb function? Yes, can you try?
Tungsten filament, sir.
Tungsten filament is there. Good.
Heating
You are heating it. You have a tungsten filament. Okay. You supply electrical energy, you supply some voltage. Then what happens to the tungsten filament? It melts and glows. Melt achina uri odinu. Melt and glow solodadu. Sorry. Pesunadu nalladhu. It gets heated up. First of all, it gets heated up. It gets heated up to the white hotness. It gets heated up to white hotness. See, generally when you have red hotness, on the other hand you might have seen the electrical heaters. What is the material used there? Can somebody say? Nichrome. Good. Nichrome is the electrical. It is a nickel alloy basically. Okay, nickel chromium alloy. Nichrome it is also a resistance. The resistance wire is made up of nickel chromium alloy called nichrome. There, what is the temperature that it reaches? It reaches the red hot temperature. When you want heat, you want it to reach the red hot temperature. When you want light as an output, you want it to reach the white hot temperature.
Can you see the temperature, sir?
What?
Can you see the temperature?
You want me to tell the temperature approximately? It will be about 1900, 1800 degrees centigrade. No, it varies for various materials. They reach the red hot and white hot temperature at various values. Certain materials may not reach the white hot temperature at all. They may melt before that. Do you understand?
So whether white hot is greater or red hot is greater?
Generally, white hotness temperatures are higher. Okay, you reach the white hot temperature at a more elevated temperature, right? In steel, you may not reach white hotness at all because before that it would have melted. After becoming red hot, it might become yellow. See, there is a whole technology behind it called pyrometry. Pyro means, can somebody literally? Huh? Pyro. Okay. Basically, the technique is based on the color of the metal. Based on that, you can even get the temperature. Okay. So here you heat it to the white hot temperature. Okay. And at that temperature, it should not get oxidized. So you enclose it in a proper vacuum or deny it of oxygen, because otherwise it will get oxidized and it will break. The point where it oxidizes, that becomes a weak spot and it breaks. So this is the whole process of getting light by passing electricity. Now, is that process fully understood? For a filament bulb, the process is fully understood. You pass current and voltage, you provide voltage, the cross section is designed in such a way that it reaches that particular temperature. And it remains at that temperature for quite some time, and after that, it might get oxidized and lose its connectivity. You enclose it in a vacuum. The whole process is completely understood. Now similarly, for the new technology, is the process completely understood? Why we should understand the process? Because we want to control the process so that we land up with certain desired performance. We want to control the process in such a way that we land up with a desired performance. So we want to control the process and the critical parameters controlling the process are to be perfectly identified. Now, are the safe operating latitude and sensitivity of the parameters known? Now, how much I can go? Up to what voltage I can subject it to? Pardon? No. If it is a filament lamp, what is the voltage up to which I can subject it to? Can it be something between 160 and 280? Now the safe operating latitude, because I cannot be very precise. So do I have a leeway? The power fluctuates, the voltage fluctuates. So do I have a leeway? So on the safe operating latitude, that is the range within which I can operate, and the sensitivity of the parameters is known. Have I studied it fully? The fourth question to be asked is, are the failure modes identified? If it is going to fail, please believe me, when you design, we start with the premise that everything is bound to fail. It may look like a very defeatist outlook. But please believe me, because it is a reality. Every designer has to start with the premise that everything is bound to fail. If things are bound to fail, then are the failure modes understood? Can you tell me what do you understand by failure modes? This is one of the failure mode. I fail. When you sleep, I fail. This is one of the failure modes in lecturing. Do you understand? Get out. Now why should I worry about the failure mode? Because once I know the failure mode, I can contemplate what is the effect of the failure on the rest of the system. So you have to identify the various failure modes of the product. We have to see whether these failure modes are completely known. Next, does the hardware exist that demonstrates positive answers to all the above questions? Now it is not good enough that somebody with his theoretical knowledge says yes to all the 4 questions. Is there any proof in the field? Is there any product functioning which proves the technology answering all the 4 questions above as positive? Probably I will give you an example which is very contemporary and relevant. Then you will understand the power of this tool. Is the technology controllable throughout the product's life cycle? Is the technology controllable throughout the life cycle of the product? For example, LED, I say, when you have an LED light, okay, one of the important questions that needs to be addressed is, does it emit any ultraviolet rays? Because it emits light, fine. But what is the range, the frequency range of the lights emitted? If it is emitting ultraviolet rays, you have to detect it. And what is the risk with ultraviolet rays? Is it just affecting skin or it can cause skin cancer? So what I need to do is, the light spectrum emitted by an LED has to be analyzed. What is the frequency ranges? If it is having some harmful emissions, so that is what I mean by is the technology controllable throughout the various stages. I should worry about how to dispose of the LEDs. The CFLs, people are saying now that the disposal of CFL is going to be a big problem. See, people have, all the environmental activists, they opposed the filament bulb. environmental activists, they have opposed the filament bulbs. Why? Because it is highly inefficient. Okay, 100 watts filament bulb is equal to about 14 or 12 watts of a CFL. This is poor. The light emitted by a 100 watts filament bulb is less than the light emitted by the luminescence given by say 12 watts CFL bulb. Fine. People have started using CFL bulb. But the disposal of CFL bulbs, they have a huge life. CFL bulbs, they came into Indian market about 3-4 years back. Now the life is also larger. Now you have many fused CFL bulbs. Their disposal is a big environmental hazard today because they contain large amount of mercury. So, is the technology controllable throughout the product's life cycle? This is the catch. Up to disposal, is the technology controllable? This is what we should bother about. The entire product life cycle has to be reckoned, and we have to see whether the technology is controllable. Let me tell you another case. Instead of just seeing about filament bulb and CFLs and LEDs, let us take something which is having political overtones also, but as engineers we are duty bound to analyze this. Recently, not so recently, the government of India decided to go for a very ambitious nuclear power generation program. Nuclear power generation is a new technology. Nuclear energy is a new technology. Okay, I don't know whether the powers that be at Government of India or Tamil Nadu government, they did it. Let us try to do a technology readiness assessment for nuclear power. Because that helps you to understand the technique. I'm not going into the political dimensions of it. I'm exposing you to a particular tool. The power of the tool can be realized when you try to do a serious technology assessment. Nuclear energy is a new technology. We want to make an assessment about this new technology. We want to assess the readiness of this particular technology for implementation. As the name itself says, it is the technology readiness assessment. Is this nuclear energy technology ready for implementation? Is it okay? Let us ask the first question. Can the technology be manufactured with the known processes? Yes, of course. Not with the known processes in India, but with known processes all over the world. This technology can be manufactured. When you have fissionable material, a critical mass, it generates enormous amount of heat. That heat can be converted into electricity and it can be used for the purpose. So the technology can be manufactured, absolutely no doubt. Are the critical parameters that control the function identified? Are the critical parameters that control the function identified? Yes. The critical parameters that control the nuclear reaction are well studied and they are very well identified. Okay, in my design, I can control in various technology. Okay, in various fission technologies, the critical parameters that control the chain reaction are understood. The first two questions, yes. Are the safe operating latitude and sensitivity of the parameters known? Are the safe operating latitude and sensitivity of the parameters known? The answer to this question is no. Now, how much of, in a sense, I can give you the values, but the whole process is not very easily controllable. It is a highly sensitive process. The nuclear reaction is a highly sensitive process which cannot be put on hold. If only we could say, let not nuclear reaction take place for 10 minutes, the whole problem in Fukushima could have been solved. It is as simple as that. I cannot stop the reaction even for a fraction of a second. Have the failure modes been identified? They have been identified, but they have been proved wrong. Japan is a country which is known for its quality consciousness. They have not contemplated the failure mode that had taken place at Fukushima. They have not contemplated the failure mode that happened in Fukushima, and that is the reason behind the whole tragedy. The failure modes, they have not been identified. It keeps on throwing suspense after suspense. Surprise after surprise. This is what has happened in 3 Mile Island. This is what has happened in various other Chernobyl, and this is what has happened in Fukushima. It keeps on throwing surprise after surprise. The failure modes, we cannot say they have been completely identified. We cannot say that. Does the hardware exist that demonstrate the positive answers to above 4 questions? Hardwares do exist which demonstrate, which gives negative answers to many of the existing questions. Okay. Is the technology controllable throughout the product's life cycle? No. We have not mastered the technology of disposing of the spent fuel. People are thinking of very crazy ideas, drilling huge mountains and putting them inside, or putting them in lead containers and then dropping them in deep sea. Okay, even sending the spent fuel to space. These are all the items that are contemplated. People are still, these ideas may look crazy, but we are implementing the first 2. Okay, we don't know, we are creating monsters. We don't know how to deal with them. The spent fuel, we really don't know how to deal with them exactly. So, this technology or readiness assessment technique, it is very generic. It can be used in multiple situations, in multiple problem solving environments. Is it okay? Now, I have spent so much of time on this. There are other 2 important techniques, we'll go to that. Go, no-go screening. Now, here what we do is, we have various concepts, concept 1, concept 2, etc., concept n. Then you have the customer requirements. Customer wanted many things. Ultimately, please believe me, the product design is to meet all the customer requirements. So customer requirements are listed here. You have various concepts. If it meets the customer requirement, answer it as Y. If it is not meeting the customer requirement, say it is not meeting the customer requirement. You evaluate the various options, the various concepts, and arrive at the one that suits your requirement best. So this is a go, no-go screen. In go, no-go screening, there are only 2 options. One is it satisfies or it doesn't satisfy. It either goes in or it is not going. In metrology, in inspection also, we use a particular technique. If the diameter, if the dimension is acceptable, it is go. If the dimension is not acceptable, it is no go. In inspection, if a particular product is acceptable, it is go. If it is not acceptable, it is no go. In inspection, in inspecting components, we use this technique. The same technique is used to evaluate the various concepts. A concept is acceptable for the customer based on a particular trait. Then it is accepted, otherwise it is rejected. So you arrive at an overall evaluation and choose a particular component which satisfies the maximum customer requirements. Next slide is the last one. is the decision matrix method. It is an improvement of the go, no-go technique. It is an improvement on the go, no-go technique. It is a very comprehensive method. It gives you an option to quantify the performance. Now it is a four-step process. Choose the criteria for comparison. Please believe me, people used to say only comparison on what basis? You are going to compare four options. On what basis? So you have to select the criteria for comparison. So where can you arrive at these various criteria? It can be from technical specification, it can be from the voice of the customer, but arrive at criteria that are going to be used for comparison. Now, then this is the first step. So I am going to compare the four alternatives based on these criteria. I can select 10, I can select 50, I can select 100. You arrive at the criteria to be selected. Then select the alternatives to be compared. So there can be 100 options that have come out of brainstorming or whatever tool that you have used. Select the options, alternatives that are going to be compared. So the criteria, it forms the various rows, and the alternatives are going to form the various columns. Generate scores. Generate scores. That is, for example, particular criteria, say aesthetics, how good looking the object will be. This is the criteria the product will be. How good looking the product will be. This is the criteria. I have three options. 1, 2, 3. So you give score. The score can be +1, -1, 0. It can be +1, +2, +1, 0, -1, -2. What is +2 means here? +2 means very good. +1 means good. 0 means fair. Okay. -1 means bad. -2 means very bad. So the looks, how the product will look, can be evaluated between -2 and +2. Or it can be evaluated between -5 and +5. Or it can be evaluated in between 1, 0, 1, 0, -2. How to choose? It depends on, because certain things there is no point in using so much of a very fine scale. In certain things it is worth going for a very fine scale. The evaluator has to take a call. He has to take a decision. And you generate scores, then you compute a total score, arrive at a particular choice. You understand? Also, here another possibility also does exist. You also use a weight for, you also give a weightage for a particular criteria. For example, in a particular product, aesthetics may not have a particular weightage. Some other thing may have a particular weightage. I'll give you the table, and then probably you'll understand better. Next slide, please. So this is the decision matrix method I have identified. I have also attached a particular weightage for each criteria. 7 means that is an important criteria. 1 means criteria 2 is not that important. Or rather, I am saying that criteria 1 is 7 times more important than criteria 1. So like that, you attach different weightages for different criteria. Then you have the various concepts. Concept 1, concept 2, concept N. Okay. Here I have used plus or minus. It need not be just plus or minus. It can be from -3 to +3. It can be from -2 to +2. Or it can be -1, 0, +1. It is your choice. Then you can, if you are using +1, -1, you can have a total plus, total minus, total. That means this plus this will give you the total. Then I can also have a weighted total. So based on the total or the weight total, you we can make a decision whether a product is acceptable or not. So these are the different ways by which the comparisons can be, the various concepts can be compared and an evaluation can be made. Is it okay? By next class we enter into the third stage of the design cycle, that is the embodiment design, actual design implementation. We will see that in the next class. So today I have, is there any questions you have, any doubts? Any questions, any doubts you have? Shall we proceed? Now I have a very interesting product within quotes discussion today. I got curious because I happened to travel through Mount Road 1 week back. The whole landscape remained changed. Okay. And I was surprised to know that a tunnel is being done under the Mount Road as such. Okay. I became curious and then I wanted to know what is the technology behind all this happening. The machineries are getting imported from Japan. I don't know what they are doing for Chennai. Hitachi is one of the major players manufacturing these equipments. So what these tunnel boring equipments, what they look like, what they do, how they work, I just wanted to know, and I got some interesting videos. I thought I'll share them with you. Okay, please see that, and I will also try to, it has an audio. Okay, listen to that carefully. Today we have time, we can even see them thoroughly so that you understand better. First one.
Because diameter cutting head with 58 roller cutters of a ton. This is the 9 meters diameter cutting head with 58 roller cutters of a tunnel boring machine, or TBM for short. This animated sequence shows how the so-called gripper functions. The automated gripper presses against the rock at the sides. The rotating cutting head is pressed against the tunnel face with a force of 26 tons. And under that pressure, each roller cutter chips the solid rock away. The broken rock falls onto a bucket wheel and is then transferred onto a conveyor belt behind the cutting head. While boring goes on, securing work is carried out under the protective roof immediately behind the cutting head. Here, for example, 2 anchor drills with independently maneuverable drilling carriages are being used. They are drilling holes into a rock for anchors which can be up to 4 meters long. Another example is a mesh placing machine. This travels over the anchor drill and places steel mesh behind the protective roof to give protection against falling rock. Which securing measures are most effective against rock falls depends on the local geology. In one place, steel anchors are best, whereas in another it may be steel mesh, caps or arches. Another means of securing are steel arch segments. The same mesh placing machine pre-assembles them under the protective roof. The complete ring is then transported to its final position, pressed against the rock, and installed there. It would now also be possible to secure with concrete, but we'll come back to that later. When the TBM is working in hard rock, it uses a so-called gripper to press against the rock on both sides. Each stroke of the gripper takes the drive forward another 2 meters. The backup train moves forward with the boring machine. At the end of the stroke, the gripper is retracted, moved forward to the new position, and then tensioned again. The TBM can now cut another 2 meters. Here we see, speeded up, how the feet are raised and lowered. When the second and fourth foot are raised, the backup train moves forward. When the first and third foot are raised, the cutting head drives forward. Here we see the view from above. The hydraulic mechanism releases the gripper for it to move forward. Then it is tensioned again for further boring. The TBM can drive up to 40 meters per day. Hydraulic cylinders control the horizontal and vertical position of the cutting head. This makes it possible for the TBM driver to steer the direction at all times. The shotcrete robot now finally secures the finished tunnel walls. From the boring head to here is a distance of 60 meters. The backup train consists of all the installations and materials needed to supply the boring machine and remove the excavated rock. It is like a moving factory, 410 meters long, which is about as long as 4 football pitches joined end to end. This TBM was specially developed for the hard rock of the Gotthard. 50 of the 57 kilometers of both tunnels will be excavated with tunnel boring machines.
So the next video is about the Bangalore Metro Rail project.
City, the usually bustling highway now stands still. A convoy of 5 trucks awaits the green signal to enter city limits. The city sleeps, unaware that this convoy carries the answer to the residents' everyday traffic problems. This is the state-of-the-art tunnel boring machine, or TBM, which is going to drill the underground sections of the Bangalore Metro. The 17-month process will drill a tunneling line stretching 4.8 kilometers from Majestic Station via Central College and the Nansauga to the cricket stadium, with the last section drilling from Majestic Station underpassing a railway track ending at the city railway station. B.S.ABDUR officials wanted to ensure that the disruptions caused by the building of these stations were minimal.
It's precisely the fact that it's in the middle of the city that we decided to go underground. There were certain sections where you cannot have elevated lines except at great destruction to the people on either side of the road. Apart from that, there is also a legacy to protect.
The contractor for the Bangalore Metro underground construction is the CEC Soma CICI joint venture. While Soma works on the construction of the 4 underground stations, the Continental Engineering Corporation and its subsidiary in India, CICI, works on the tunneling process. With years of international expertise in building tunnels, high-speed rail, bridges and highways, and after meeting success with the Delhi Metro construction, CEC now brings the TBM to the Garden City. The convoy is making good time, but it must reach Majestic Station before 6 a.m. to avoid the morning traffic. As the TBM had to be custom-made for Bangalore's geological conditions, a series of tests were carried out in manufacturer Hitachi Zosen's factory in Osaka, Japan. A visiting team of BMRCL and CEC engineers carried out the final inspection before the TBM was disassembled and shipped to Tamil Nadu, where it was loaded onto 28 trucks.
Hitachi was a wonderful experience, and as the head of this organization, I learned a lot. My colleagues learned a lot in organizational behavior and group dynamics.
The convoy, after traveling 7,500 long kilometers, finally stands at the Majestic Station at the break of dawn. There is excitement in the air. A shaft 28 meters long, 22 meters wide, and 16 meters deep is ready for TBM parts to be lowered into. Assembling the parts is going to be no easy task. Months of preparation have led to this moment, and all the workers have been trained to handle equipment and to follow safety precautions. The first part to be lowered is the front body lower section, which is the foundation piece around which all the other units are bolted. Overseeing the assembly process is Project Manager Russell Brown.
The second part of the lower end shaft, that weighs approximately 56 tons, and that's called the drive module. This section needs to be turned over into a vertical position. To do that we use two cranes. One of them is a 350 ton duty crane, and the second one is a 100 ton assist crane.
Here, communication poses a greater challenge, as interaction with the crane operators is only possible through hand signals and radio. The third module is the front body upper part, which is now fitted on top of the front lower body, wrapping around the cutter drive structure. Then, 10 cutter drive motors and a decompression chamber are fitted onto the driving module.
We often inject an air pressure up to approximately 30 psi. This pressure is equivalent to what you would put inside of your car tyre. If you took this car tyre and put it inside of the cutter chamber, it would actually go flat because of equalising the pressures.
On the 29th of April 2011, fighting with the Bangalore rains, the engineers lifted and lowered the cutter head. Post-cutter head positioning, the articulation section is bolted on, which allows the TBM body to be angled by degrees. The middle body rear side section, equipped with the 16 thrust rams, is then fitted into position. These are used when building segments or when pushing forward during excavation. Attached to this middle body is the slurry inlet and outlet pipe, which helps in carrying the drilled mud to a recycling plant on site. Here, coarse gravel and fine particles are removed, and the resultant slurry is then sent back to be used for tunneling. The final component is the rear body section with segment erector. This unit is fitted to lift and place the tunnel segment into the correct position before thrusting forward. These segments are manufactured in a plant in Pune industrial area, where over 100 construction workers help manufacture segments at a speed of 12 segments per day to meet the 21,120 segments requirement. With this, the TBM stands completed, weighing a total of 350 tons.
BMRCL is new to tunnel. Bangalore Metro is new to tunnel. Number Metro is new to tunnel. CEC is not new to tunnel. And we are quite confident about the ability of CEC. So CEC has got all the experts. And we are willing to share. And that's the good thing about this partnership as it begins to fly.
So a similar exercise is going on in Chennai also. They have started the process. Now, see why we are doing these product case studies. Now the idea is to create some, because engineering is some exciting challenges. Engineering poses many exciting problems. And finding solutions to these problems is engineering. Okay. What we are trying to do in these product discussions are just throwing problems before you so that you will get enthused and look into these issues at greater depth and detail. Is it okay? Have a good day. Thank you.